that I have presented so far. The only algebra complexity lies on the integration, yeah, the integration part. So with today, if I'm going to show you the second. I mean, I promised before that I'm going to show you two different methods. It's not really a different method. It's just handling the coordinates differently. So I have presented the Cartesian. Okay, I presented the Cartesian. So I mean in x y z. So what I mean is in x y z components. So I'm going to present to you in cylindrical components. So now, how many of you have questions regarding the solutions? I mean, regarding the analysis that I have walked through. I walked through with you on this, because understanding this. So as I put it in the Google Classroom, I mentioned that understanding this is going to help you in the other part of the course. Okay, so one is the understanding is, I mean, what I'm trying to tell you is the understanding part is all this. If we look at this carefully, we are treating the line. I mean, we are treating the line charge as a continuous discrete point charges, continuous discrete point charges along the line, right? So I have mentioned some of the idea, some of the concept here, so that you need uh if let's say we have many point charges here, then each of the point charges contribute to this point P here, and we need to sum all the electric fields. So here the integration just basically represent uh the line charge is continuous, right? Is continuous is, and there is the assumption as well. There's one assumption as well, that the charge distribution is uniform along A to B. So here, I mean, first is this concept of this integration here, because before we come to here, all other calculation is based on a single point charge. Yeah, one, I mean, 1 to 1 or many to 1 point. So we are calculating at a point. So for example, for these slides here, so we have uh, different point charge in different location, and we want to find the electric field at a point. So we have applied this based on Coulomb's law. And here as well, uh, the I mean the formulation of the problem. I mean the formulation of problem is also based on Coulomb's law, basically. But of course, we treat it as continuous instead of a discrete. So that is the first concept that I wanted you to understand. The second part of it is more towards of the maths. Yeah, it's more towards the maths part. This is one way I've shown you by integration by substitution. So I show you the techniques of how I convert one form to another form. Okay, so this is going to be applicable in most of the problems that you will encounter in the tutorial, as well as in examination. Yeah. So now I want to ask you, is there anything that, is there any part that you would want to clarify? Things that you are not so sure. So please let me know now. Please let me know now. So I will let you guys, to have some thoughts on it, about 5 minutes. So in 5 minutes time, if no questions, okay, I will continue with where I left. So I will continue with where I left. So I'm going to show you the second approach. Yeah. So the first approach is using Cartesian. So I'm going to show you the second approach. Okay, so if you have no questions for now, then I'll proceed with the second approach. So I hope everyone is awake. I know it's morning. I know it's in you are still in holiday mood and so on. Same goes for me. Yeah, but I mean your responsibility is to learn. So my responsibility is to teach you as much as possible. So I need you to focus, and this is important, as I said. So if it's not important, I will emphasize. I mean, so whatever I presented to you, as well, um, I hope you understand, especially the steps, the method that I've applied, and I that's why I always ask, do you follow? I mean, if you do not follow, then I will have to repeat the steps that I have shown you. So that's the reason why I asked you to study the solution. So I'm not sure how many of you have studied. Okay, maybe none of you, or maybe a few of you, or maybe all of you. So my hope is everyone have studied it. Okay, so I'm going to show you now the second approach. The second approach based on cylindrical coordinates, so cylindrical coordinate vector system. So nothing. It is nothing much more than, I mean, the techniques of solving using cylindrical is nothing more than Cartesian. I mean, the way that we approach it. So first, again, here is our point charge. So this small length here. So this small length here, we treat it as a point charge. Okay, that contributed to this point xyz. They contributed to this point here xyz. The electric field, okay, at this point here. So we have a line charge A to B. Line charge from point A to point B. It's a finite. It is a finite line charge. So then it is. So I have presented to you the infinite result. I mean the result. If let's say A extended to negative infinity, B extended to positive infinity. So there's one special case. So we are going to analyze it as well, and we can compare both cylindrical and Cartesian. So first, we treat this as a finite line charge. Okay. Here now, as I said, the approach is the same. So we will take an arbitrary point. We will take an arbitrary point along. So we will take an arbitrary point along A to B. So any arbitrary point. So this is arbitrary. This vector line here, the vector from this arbitrary point to the point of interest where we want to find the electric field, the R is also arbitrary. Yep. So I will write it down first in Cartesian. Okay. So this point is fixed. Yeah. So that's why it's Z minus Z. Yeah. So this point is fixed. Okay. This point is fixed. Yeah. So at this point is Z, right? So Z minus Z. Okay then. So how are we going to change it to cylindrical? Yeah, at this point here. So you we can so I can easily say is that this is actually rho or R. Okay. So I will say that okay, this is rho, so which is the radius, which is given already. So you can see that the parameter here, which is the cylindrical coordinate radius rho. So let's say at I would put this as r cap, okay, plus z minus z cap. All right. So if based on your knowledge that cylindrical in cylinder we have let's say rho, phi and z, right? So where is phi? So I didn't see any phi here. So why is that? Okay. So I'm going to show you why now. Um, so I'm going to bring you back to the Cartesian to cylindrical conversion. So uh, I just copied the transformation just for your easy reference. So this transformation here is from Cartesian to cylindrical. So we can see a index r, a index phi, a index z. So all these index are referring to the radial component, the phi component, and the z component. And a of x is referring to the x component, y component, and z component. So I can basically write this. Let me just adjust a bit. So I can actually write this in a matrix form. Okay. So I've already shown you as well how one can change from Cartesian to cylindrical vector transformation. I have shown you that based on the unit vectors. So now how are we going to transform it into cylindrical? Okay. So we will define. So here we will define that. So this is the define here rho. So as I said, this define. So this is actually equals to square root of x squared plus y squared. Okay. So this is define. And phi, what is phi then? So phi is actually arctangent. If based on our coordinates, phi is y over z, right? Sorry, y over z, y over x, right? So if we let's say we drop down this point at this point here, so this is phi. So the length here, so the length that uh projected to x. So this length here is x, right? So this length here is x, this length here is y, right? So phi is arctangent y divided by x. Okay. So I want to basically show you how I obtain rho r cap. So as I said, the r cap referring to the cylindrical vector coordinates. Okay. So you don't need this. So bear in mind, this is phi. So tangent phi is y over x, right? Okay. Now, so what is the value of ax now? So ax is x. So x, y, and z. Okay. So now, so therefore, sorry, I write this wrongly here. So it's supposed to be a of r here. So expanding this, so here we find that a of r is actually x cos phi, okay, plus. So this is the r component, or so we so call the r component. So sine y sine phi, and a of phi is negative x sine phi plus y cos phi. And here we have a of z is z. Okay, sorry, it's not z here. It's z minus z. Z minus z prime, so which is the z component. Okay, so I just substitute the value for, I mean, the magnitude of the x component, y component, and z component into ax, ay, and az. So these are the x, y, z components respectively. Okay. So bear in mind, cos phi, how we translate from here, cos phi and sine phi. So basically, so so we will focus on AR and A phi because A of Z is Z minus Z. So the Z component doesn't change. So cos phi is basically x over square root of x squared plus y squared plus y. Sine phi is y over square root of x squared plus y squared, right? So this is going to be um, so x squared plus y squared. So it's going to be rho square over rho. So which is rho, right? So just sorry, let me just write properly. So it's x over square root of x squared plus y squared. So this is going to be x squared plus y squared divided by square root of x squared plus y squared. So from the definition, x squared plus y squared is rho. So the numerator is rho square divided by rho, so equals to rho. Yeah. So this is by definition. So a of r, that means our radial component for the cylindrical coordinate system is rho now. Okay. So why is it cos phi is x divided by x squared plus y squared? So from here, so this is phi. So tangent phi is y over x. So y x. So this is x squared plus y squared. Okay, so we have the r component now. So what about the phi component? So the phi component then, uh, negative x sine phi. So y cos phi, right? Okay. So we have negative x sine phi is what? So is y divided by sine phi is y divided by square root of x squared plus y squared. And y cos phi is x over, so equals to 0. Okay. And therefore now r, so as I have written here, so r now, the r vector which represent this vector here, which I have written here as well, is represented by rho r cap plus z minus z cap. So that's the reason why there's no phi component. The phi component is equals to 0 now. So so the magnitude now, it is the square root of phi square plus z minus z prime square. Okay. So the electric field at the point now can be represented by rho r cap plus z minus z prime z cap. Okay. All right now. So I hope you still, I mean, you still remember the form here, because why is it three? The power is 3/2 because of this, right? I have mentioned this before. Okay. So this is the magnitude. So this is the magnitude here. Magnitude cube, right? So magnitude is square root. So therefore it is cube 3/2. So we have the r component now here. So coming back to our solution. I mean our approach here. Okay, so how are we going to? I mean, again, we are going to use. We have to solve the integral. So we are going to use variable by substitution, and I'm going to use the variable presented in this diagram. So which is sorry, phi alpha 1, alpha 2. Yeah. So I'm going to use the variable given here, okay, to represent the point A and point B in terms of alpha 1 and alpha 2. So which is obvious that the integration limits is from alpha 1 and alpha 2. But 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 before that, I mean before I put this limits, in terms of alpha 1, alpha 2, so we have to transform first, right? Um, so I'm so z prime, okay. So we can see that z prime, so which is a variable, okay. At this, I mean this is a variable point, right? I mean, even though I mentioned that this is arbitrary, we can choose arbitrarily, and this point can be anywhere. So therefore, it's a variable point. It's represented by here to here. So how are we going to locate this point in terms of I mean how are we going to relate this point to the variable alpha? Sorry, yeah, alpha. Sorry. So basically is this length here. Basically is this length here minus this length, right? So this length from origin to point T, from origin to point T minus this length, right? So that is how we read uh, at this point. So therefore it's OT minus, so this length here is what? Tangent, phi tangent. So it's rho times tangent alpha. So it's rho times tangent alpha, right? So I'm going to differentiate dz prime. So this is going to be negative rho secant squared alpha d alpha, right? Okay. Um. All right. So for this term here, it's going to be rho secant squared alpha. So I'm going to write component by component. Um, Oh, sorry. There's one more. Um, okay. Um, wait. My apology. So I think I write it in the next slide. It's easier. So it's a bit convoluted here. So I need some space. Um, sorry. Let me just adjust again my writing. So I want to. I just want you to see the whole expression. So I'm going to write separately so that I mean you will see why I write it separately later on. So this is Z, sorry, R cap dz prime, and also okay. So I mean here we will see that rho divided by rho squared plus z divided by z prime square. So this part here is going to be, this is your R, right? So if you see carefully, this is my R, right? Rho divided by R is what? Rho divided by R is cos phi, right? So this part here is your R, right? So which is written here. I mean the magnitude of R. This is the magnitude of R. So rho divided by R is cos phi. Okay. And for this term, the next term here, Okay. So I'm just so that you can see it more easily. So I don't have to go back and forth. So I paste this for your convenience here. Uh, okay. So as I mentioned, R is this term. The magnitude of R is this term here, right? So maybe I just write here. The magnitude of R is square root of rho squared plus z minus z prime square. Okay. And z minus z prime, so which is this length here now, right? Z minus z prime is this length divided by r is sine phi. So I can write this electric field now in terms of um, so it's going to be in terms of cos phi, and also sine phi. Why I always say phi? Sine alpha, sorry. Okay. So we as I said, I mean I'm going to use all the variable presented here. So I haven't substituted dz prime here. So which is going to be negative rho secant squared alpha d alpha. And if we substitute z prime, sorry, if we substitute z prime as this, right? So rho squared, so it's going to be secant, so it's going to be, this term here is going to be rho secant squared alpha as well. Okay. Okay. So it's going to be sorry, it's a bit lagging. Okay. So now, here, what I mean in these steps here, I have substitute dz prime, which is negative secant squared alpha d alpha into the integrals. The electric field in the integral expression. So I replaced this. So here's goes the same as well. So rho squared plus z minus z prime square is what? Is I mean, if you're going to use this, it's going to be, I mean, secant squared. I mean, if you substitute this, I mean, z prime into here, so you're going to obtain rho squared secant squared alpha. Okay. All right now. So this, as I mean, the numerator and denominator, we have some common terms, so which is secant squared alpha. So we can cancel off this. Rho and rho divided by rho squared. So we can also simplify this into rho. You can simplify this into rho. So we can rewrite this now as cos alpha r cap plus negative, so it's minus, both are negative, okay. So here are all simplified, okay. And what is the limits now? So it's alpha 1 to alpha 2. And we have now so using this limit, so it's going to be sine alpha 1, alpha 2. And here will be negative cos alpha, right? Okay. So basically we have obtained the expression for the electric field um, for the finite line charge. So, well, now again, if so the special case, so we now come back to the special case. So we now come back to the special case where S B, point B, tends to positive infinity and A tends to, sorry, tends to negative infinity. Okay, so as point B and point A goes to in the it goes into the goes into the direction of infinity. So I want you to look at this diagram again. Okay, so alpha 1 is a measure. So let's say you are at this point here. So this is the observation point. Okay, so as this point move as this point move to infinity, right, and this point move to infinity, this point move to negative positive infinity, B move to positive infinity, and A move to negative infinity. So alpha value is going to be, alpha 1 value and alpha 2 value tends to 90 degrees, right? Tends to be 90 degrees, right? Am I right? So if this tends to infinity, so if you here, if you're standing here at this point here, so if you look at it, so with respect to this, with respect to where you are standing, okay, so that means this is 90 degrees, right? If let's say at infinity, and same goes for this one. It's going to be 90 degrees as well. So as so this tends to be alpha 2 tends to positive 90 degrees, and alpha 1 tends to negative 90 degrees, right? Here we can write now. Here we can write this as, so alpha 2 minus, so this is 90 degrees. So it's pi over 2 minus negative sine negative 90 degrees is going to be, sorry, why I'm writing pi over 2. So this is going to be 1 minus 1. And cos alpha minus cos alpha 2. So if 90 degrees is going to be 0, right? This is 0. Cos 90 degrees is going to be 0. And negative 90 degrees also is going to be 0. So the z component, there's no z component. There's only r component. Okay. Okay. So it's about time now. All right. I will stop here. Okay. So we are going to meet later again for our replacement. So um again, I will post this again. I will replace the new one. So in the meantime, please go through the solution again, between both I mean for the solution that I presented here for both Cartesian and cylindrical. So please go through again uh, the steps and the explanation. I mean, from the steps that I presented, please go through it again. If you have any questions, by then, later we are going to meet at 2. So please ask me during that time. All right. So I'm going to stop here. Yeah. Thank you, everyone. Okay. See you guys later. Thank you. Bye.